on this computer. Yeah, we're going to get started with this workshop. You're all very welcome to the Dublin Data Science workshop series on an introduction to Bayesian statistics and buy till you die models. This is the 6th, I think. We've run one most months. Yeah, I think this is the 6th. I think we missed 2 months. And the idea was to give a talk I've been given for a few years now on how to use Bayesian data analysis, how to use modeling, all that kind of stuff. But one of the reasons why I'm doing it this way is I always found that a lot of the examples were a bit kind of toy and didn't give you a good sense of how and why these techniques are quite powerful and how they could be used to solve a real world problem. And I'm sure most of you have been here before, are sick of listening to me repeat this, but we gave a workshop series last year on customer lifetime value and customer transaction retail stuff. My plan was originally to build these models, but they proved to be far too sophisticated for what we were trying to cover. And I thought, you know what, I will just drop out. I covered them very briefly, and then they can be the focus of a full kind of Bayesian approach to these models. So just before we begin, and just to get everyone used to the chat and all that, because I do try to make this reasonably interactive. And while I only have a single screen, unlike normal, I do, Neil, who's a regular participant at our meetups, is just going to keep an eye on the off chance that I don't see someone's question. If you have any comments or questions or anything like that, please put them into the chat. That little bit of feedback is great for me, so that it means I'm not just talking into the void. The other thing to mention is that the Wi-Fi here can be a bit, actually the internet connection, I should say, not the Wi-Fi, can be a little bit unreliable. I'm hearing, like I said, I'm on the mainland United States, and I've definitely noticed a difference in both the quality and the reliability. It's not terrible, but you just can't depend on it not going out for like 20 or 30 seconds. If that does happen, I'm just going to keep going, and anything that's missed will be on the recording, and you can catch up, and I can repeat on whatever I said once we come back. When it does go out, it only tends to go out for 10, 20, 30 seconds. It's not like it's going to be a 10-minute outage. We've got a question straight away. Yeah, may I know the name of the YouTube channel? Yeah, I think if you just go to youtube.com and Google Dublin Data Science, there's a Dublin Data Science channel, and basically most of the online talks that we've done since COVID are on there. I think all of them. I can't guarantee all of them, but I think all the ones that we recorded certainly are up there. A bunch of workshop series are up there, and the previous 5 workshops of this are all up there, and this one will go up probably tomorrow or the day after. Once it takes a little while to render it into HD and all that kind of stuff. Okay, so okay, we've got about 13 people, well, 10, 11 including me. I recognize a lot of very familiar faces and names. Is there anyone here that is completely new to this workshop series, or Dublin Data Science in general, or anything like that? Is there anyone that hasn't been at any of these workshops before? If they are, could you just say something in the chat so I have a rough idea? I think there's one. Okay, that's fine. And so I'm going to do what I always do for these is I'll do a quick, and everyone who knows me about being quick, it's difficult. I'll do a quick, say 10-minute, 15-minute summary of where we are, because that tends to lead into what we've done, and a quick summary of like what we've done in the previous workshops, and then we'll dive into the new content that we're going to cover today. And again, I'm going to do it quickly, but if there's any questions or anything, I would much rather be answering questions rather than just blindly going through the material that I decided to prepare for tonight. So I have no problem at all, hitting pause and addressing specific questions. So don't be shy about interrupting me. Just pop a question in the chat, and I'll try to address it. Now, there are times that, like, you're asking a question that I'm about to get to, or is a massive diversion for what I want to talk about. In that case, what I sometimes will do is either park it for the break or until the end, or like get to it a little bit later. So just bear that in mind. For those of you who aren't familiar with the format, I'll just, if you have a live transcription, that might be in there. I think YouTube's got pretty good at that, although it's trained on American accents, so non-American accents can be notoriously hilarious in terms of the transcription. So yeah, have at it. I've never actually tried that. I must try it. I do know that when I go into the various, liquor stores and subway shops and stores and whatever, people have difficulty understanding my accent, which can be quite funny. So I generally let either my wife or my parents-in-law do the I heard the YouTube channel. No, it's Dublin Data Science is the channel name. Dublin Data Science. Oh, thanks, Greg. Okay, so all right, so let's get started. So this workshop series is about introducing like Bayesian statistics, Bayesian modeling to a real world problem. So in the previous workshops, we kind of talked about how Bayesian statistics worked, and it's essentially it takes the approach of using Bayes rules. So the idea is that the Bayesian approach is essentially you take prior information about the way you believe the world works, you add data to it, you combine the two, and you get a posterior inference from it. And while most of us do the world does kind of work that way in general, the Bayesian approach essentially puts that on a fairly solid logical and mathematical foundation. And the key point of all of this is that what you get as a result of Bayesian statistics and Bayesian computation is you get what's called a posterior distribution, which is the distribution of the parameters of interest conditioned on the data that was observed. Okay, and in Bayesian statistics, that is the idea is that Bayesian posterior distribution encapsulates all the knowledge that you have as a result of your modeling, and anything that you want to do is derived from that posterior distribution. And that's kind of where we work on it. So, there's a load of different toy examples from it. And initially, it goes all the way back to the start of probability. Thomas Bayes, although, his stuff was quite indirect, it was actually the French guy whose name has escaped me right now. He codified it all as part of, he in the Napoleonic Army. He used it as a way to improve artillery fire. The reason why it didn't take on, there was a couple of reasons why it didn't become more popular. No, it wasn't Gauss, Marion. I'm trying to think of it. I'll look his name up I'm just blanking on it. It's a really obvious one as well. It's not Poisson and it's not Cauchy. I'm just blanking on his name. Laplace, that's it. Thank you. Yes, Simon Pierre Laplace was the guy who kind of codified a lot of it. Thank you, Marion. That was going to annoy me now for the next hour and until the break. But one of the reasons why it took a while to get going was that ultimately it involves high dimensional integration, because that combination of prior information and data, which is essentially modeled as a likelihood, you end up doing an integral there. And computationally integration is hard, especially in high dimensions, because of the cross dimensionality and all that kind of stuff. So it's only been in the last, say, 10 years, 15 years or so that like the computer science and chip design has managed to become advanced enough to do these kinds of things properly, with the advancement of things like auto differentiation and all that kind of stuff. So I've talked about that. I won't get into that into too much detail. And in the past, people kind of got around that by using mathematical tricks and what they called conjugate priors. So they basically set the problem up so that your prior distribution and your likelihood kind of matched each other mathematically, so that integration just boiled down to some arithmetic on the parameters, and you could do it very quickly. Now, obviously, in real world problems, that tends to fall over very quickly, and but we can kind of do that now. So like routinely, to give an example, in the ones we're doing today and the stuff we've done even in these previous workshops, today we're dealing with a 2000 dimensional posterior distribution that we're doing inference on, which essentially even 10 years ago was probably quite a computational challenge, and was done as part of PhD work to calculate these things. Now we just basically point Stan at it, and it kind of works. Although I guess we did have JAGs back then and WinBugs and stuff like that. So what these kind of Bayesian computational systems do, things like PyMC3 and Stan, and there's TensorFlow probability. I'm not quite sure how that works, so I think that works slightly differently. They are all just high dimensional integration engines that can perform these integrals in a computationally efficient manner, and then produce these posterior distributions for you. And PyMC3 and Stan are quite closely related. They're built on broadly similar technologies, and they kind of borrow ideas from one another. And yeah, so that's basically what we've been doing. And very specifically, what we've been working on are what are called buy till you die models. So that's kind of the real world example that we've been talking about. So it's based on like retail data. So you have basically your raw data set looks like a series of transactions, which will have, some kind of customer identifier, customer ID, some kind of transaction timestamp. It's not built into the model, but what was bought and the cost of the transaction, like what the monetary amount was. And that's kind of the basics of what we're dealing with. And from that, there's a whole bunch of different ways in which we can perform some statistics on that. And essentially what we're trying to do is turn that transactional data into something meaningful that we can say about our customers. Now, in this particular setting, we're using what are called buy till you die models. And these are used in the setting that we're talking about here. It's very typical of retail, where it's a non-contractual setting. And by that, it means like there's no regularly kind of legally mandated frequency to payments. So for example, like a non-subscription service, so yeah, an easier way to describe it is what it isn't. So if you think of like your Netflix account, or your mortgage, or your direct debit for any of those kinds of things, those are considered contractual, even if they're variable payments, because you have a regular point of time at which you interact with your customer. And those you can certainly do customer lifetime calculations on those, and I've talked about that in the past with things like survival analysis. But in this situation, you don't have that, because you don't know, and it's kind of to a certain extent at the discretion of the customer when the customer transacts. You have no real control or knowledge of when a customer is going to transact, or how, or whatever. So you kind of need a different method. And these methods, these buy till you die methods, were built by I'll get to that in a sec. Chris, sorry, you've just disrupted me thought there. So Peter Fader, he is kind of the leading guy behind all of these models. I think he first started working on these in the late 80s. He's at the Wharton School of Business. So the idea of a buy till you die model is there's a whole range of models that do this, but the idea of the overall buy till you die is that the first transaction that a customer makes with a process, with a firm, is the customer being born on the system, and then the customer essentially transacts at some kind of using some kind of predefined process until the customer dies, as in churns or leaves the service and stops using your business. And the idea is that you're modeling that kind of, how are we going to model those transaction counts, those transaction events, and also how are we going to model the lifetime? And there's a bunch of different ways to do that. I'm sorry, I'm not quite sure of the context there, Chris. What is the dropout process in the article? What article are you referring to? Sorry. Are you talking about the worksheet I'm talking about here? Oh, sorry. I'll get to that. I'll get to that in a sec. I'm about to explain that in the process. Okay, so like I said, so your idea is that your customer is born on your screen, is born on your system. So the first transaction we don't really count, because for the purposes of these models, the first transaction is essentially the birthing event. So we don't really worry about that too much, and we're not kind of modeling that is kind of a different problem. So we all assume that the very first transaction happens, and then essentially the customer will transact until a lifetime value, or there's some way in which the customer churns and leaves the system, at which point the customer stops purchasing from your system. And that's the basic idea of your buy till you die. And then how those various things are modeled is what the different versions of buy till you die do. So what we've been focusing on is the PNBD model, which is the Pareto negative binomial distribution. So the idea there is that a customer is born in the system, and at birth, they are and if you think of this as like God, the way I'm describing this is the data generating process rather than what actually happens, because no one's there, right? And customers don't think this way. But essentially, in terms of the assumptions of the model, when a customer appears on your system, they have a predefined lifetime, and they also have a frequency at which they transact. And that's a homogeneous process, which is a Poisson distribution. And so they transact at a fixed frequency throughout their lifetime. And then when their lifetime is reached, they churn off the system. Okay. And just bear in mind that the churn point, because they're kind of independent processes, the point of the last transaction and the point at which the lifetime may be different, and that's kind of one of the key assumptions of this. So you don't necessarily observe the full lifetime of a customer, because the customer will generally churn at some point between the moment you're observing the system and the previous transaction that the customer made, because you know the customer was still alive at that point, but you don't know. And you actually don't know, and that's one of the things we're going to be looking at this given point in time, has the customer churned or has the customer not churned? That's one of the key questions we're going to have to ask. And we can use that through the data that we've observed. We can make inference on that. Okay, so essentially it's modeled as two distributions. So the first distribution, like I said, is the Poisson distribution, which is just the transaction count over a period of time. And the inverse of that, just to mention it, the inverse of a Poisson distribution, we can think of it as an exponential. So if the exponential distribution and the Poisson distribution are kind of logical inverses of one another. So if you have a fixed period of time, a Poisson distribution will tell you how many events occurred within that fixed period of time. And if you have an exponential distribution, you know that or if you have a fixed number of events, the exponential distribution will tell you how much time passed between those different events. Okay, so the way we model, there's two different ways in which we can think about the lifetime as well. So we could think about the lifetime as a discrete event moment. So if we think of the lifetime as, let me start again. So we have two distributions, right? We have a Poisson distribution for the events, and we have an exponential distribution for the lifetime. And both of them are fed by a gamma distribution. So essentially, if you think of it as from the data generating process, when we get a new customer, we make a draw from a gamma distribution that gives us the Poisson rate that the customer is going to transact at. We also make a draw from a separate gamma distribution, and that is fed into an exponential distribution that gives us the lifetime of the customer. However, like I said, they're inverses. So another way of thinking about the lifetime is, rather than thinking about it as an exponential lifetime, we can think of it at every period of time. How many times does a customer drop out? If you think of it that way, right? So and again, you can have multiple counts, but you can kind of think of for like, okay, if we start at week 0, we have a Poisson rate and an exponential rate. At the end of the week, how many transactions occurred, and did the customer churn or not? Right. And that's kind of what I mean by the dropout process. Now, there are other ways of modeling that churn where it's more explicitly modeled as a dropout. But to me, the more natural way to think of this is as a transaction frequency and as a lifetime. And it just happens to be that the lifetime process, the exponential, is modeled as it's a similar parameter. You can think of it as a dropout rate rather than as a exponential. It's kind of a weird thing, and it took me a bit of a while to get that relationship between the exponential and the Poisson. Kind of is very intuitively easy to kind of, if you don't have to go into the details, you can kind of get your head around it quite quickly. But like everything else, once you actually try to use these things mathematically, it gets a wee bit complicated. And the reason why it's called a Pareto negative binomial distribution is because when you do it mathematically, and this is something I didn't really understand until I started doing this workshop, was that if you have a gamma distribution feeding into a Poisson, that is essentially a negative binomial distribution. And it's a way of creating over dispersion in a Poisson. It's essentially a form of an over dispersed Poisson. So that's where the NBD comes from. That's the negative binomial. So you can think of a negative binomial distribution as a Poisson where the gamma is generated randomly. Okay, where the lambda, I should say, is coming from a gamma distribution. And then the other way to think, and that gives you the second parameter. and the two parameters into the gamma. And then the P is a Pareto distribution, and that is because if you're drawing from an exponential distribution and your parameter is coming from a gamma, then you get what's called a Pareto distribution of the second kind. Now, I'm not going to explain that because I don't really understand it. My limited knowledge of this, I know a little bit about like heavy tail distributions and Pareto tails and stuff like that, but I know there's a bunch of different Pareto distributions. Apparently this one in particular is a Pareto of the second kind, and you can kind of see that because the exponential distribution has a long tail, and when you're also adding randomness in what the underlying value is, that the draw, so you're essentially drawing from a gamma, that gives you your mu, which is the parameterization of your exponential, and then you're drawing from the exponential. You can see how essentially if you get like the mu is out in is towards the tail, and then the second draw is towards the tail, you can see how you get kind of this long, this very heavy tail distribution that gives you that kind of Pareto effect. So essentially what we've got is we've got this over dispersed Poisson process for all the customers' transactions. And we also have a Pareto tailed distribution for their lifetime. And I guess intuitively that kind of makes sense, because it makes sense that you would have most customers would lie in, you know, a certain period of time, but then you'll have a small number of customers that whose lifetimes are way out. And what we're trying to do with this model is essentially model that process. We're creating it. So for every customer, the posterior distribution is going to produce a lambda for the transaction rate and a mu for the lifetime rate. And essentially the mu and the tau are essentially the inverses of that. And that's basically what we've been building. Now, up to this point, we've never actually combined the two. We looked at kind of the transaction rate by itself, and we looked at the lifetime rate by itself. But now we're actually going to combine the two, because when you think about it, it actually kind of makes more sense to have the two together informing one another. Because just intuitively, even though we can kind of think of them as being separate, in terms of how we observe the data, they're like both the transaction rate and the lifetime are very inextricably linked. So it kind of makes sense to model them together. Okay. So that's kind of where we're going for today. Now, does anyone have any other questions? I appreciate that might not have been the best description for it, Chris, but hopefully it'll make more sense as we go through it. Okay. All right. So I'll give people a chance to ask any questions if they have any. Pareto. Okay. Right. So one of the benefits of these approaches is that even though we actually have granular transaction data, and this was one of the reasons I believe why this model originally took off and became like useful, is that essentially the summary statistics for this model are very small. That we don't actually, for every customer, we can boil all that, because we're not modeling transaction amounts in this data set. We're literally just modeling both the customer frequency, transaction frequency, and lifetime. We don't have to worry too much about individual transactions. That's something we will probably add. I'm hoping to add that next week, in fact, or next month in the next workshop, because it's going to be, I think it's going to be instructive to see how we could do that. I don't want to promise that because it depends on where we get to. But essentially, we boil down the information into three like summary statistics of all the transactions. So we have basically the X is the number of transactions that the customer made. So remember, this is in relation to the customer's first transaction. So it's going to be one less than the actual amount we observed, because we don't count the very first one. That's considered like transaction 0. So it's X is the number of transactions so X can be 0, because in other words, the customer was born but never actually transacted again, or has a very, very low transaction frequency. Then T is the observed time period. So there's a customer is born on the system, but we're always observing the data at a certain point in time. So it's basically, you can think of capital T as being the time between the customer first transacting on your system and the point at which we're observing the data. So if the customer was born, like if the customer first transacted a year ago, then, and let's say we're using weeks as our unit of time, then capital T would be something like 52, give or take, depending on exactly when the customer transacted. Okay, and then TX, T like sub X, is the time of the customer's last transaction. So you have T0 is when the customer was born, and then at a certain point the customer made the last transaction that you've observed on the system, and you have T sub X. That's going to be smaller than capital T, obviously. I hope people understand why that is. Does everyone need me to explain why T sub X needs to be less than T? I'm going to assume not. And then we basically, and that's it. That's all we need. We don't need any more information. And that was really useful back in the day because this stuff was actually developed in the late 80s, I believe. Apparently it was developed by people trying to, and again, most of you have heard me say this before. It was done by Morgan Stanley, I think, or JP Morgan. I think it was Morgan Stanley. And they were trying to get a sense of their retail customers here in North America, you know, where there's a strong business around, you know, professionals and people who have a bit of money. They trade in the stock market. So in the late 80s and early 90s, people would just call up their broker and say, you know, I want to buy 100 shares of IBM or whatever it is. And they wanted to get a sense of, and that was obviously completely at the discretion of the customer. So some people will call a lot, some people will call very rarely, some people will literally show up, become a customer and never be seen again. And they were trying to get a sense of all that stuff. It was only later that these models kind of got moved over into the more kind of retail space where you were thinking of actual shopping and shopping transactions and stuff like that. So, okay, so we have our first, so like I said, I'm going to mention a couple of assumptions in the Pareto, the PNBD model. So we have 5 assumptions that we're going to work on. Just give me 1 sec. Let me move because, like I said, I'm working on a single screen here. So I want to be able to see everything. So we have 5 basic assumptions that we're going to work on. So a customer is born, and then once the customer is born, the number of transactions follows a Poisson process, and that the heterogeneity in lambda follows a gamma distribution. So in other words, the different customer lambdas. So if we calculate a lambda for each customer, that lambda follows a gamma distribution, which has 2 parameters, alpha and R. So shape alpha, shape R, and rate alpha. I think that should be backwards, actually. I think it should be shape. That must be a typo. Each customer has an unobserved lifetime of length tau. The point at which the customer drops off becomes inactive relative to the starting point is distributed as an exponential with the dropout rate mu. And again, so that's exponential is a bit weird that way because the parameter is the exact same as the Poisson, even though it's the inverted of it. So like the exponential has this dropout rate as its parameterization, but the mean value, which you would expect to be that parameter, isn't. It's actually the inverse of the parameter. So if you have like an exponential distribution with a mean of 10, let's say, it's actually 1/10 is the parameter you put in to get that average of 10. So that was the thing. It took me a wee while to get my head around that, and it's very easy to make that mistake and do divisions when you don't need to and stuff. But so you kind of think of the way to think of an exponential is kind of like the opposite. It's kind of like a Poisson. It's just that we're tracking the time instead of the actual counting the events. So again, the heterogeneity across the dropout rates follows another gamma distribution, which has S and beta. And then the transaction rate alpha and the dropout rate mu vary independently across customers. So in other words, there's no correlation between lambda and mu for any given customer, right? We can generate those 2 values independently of one another. Now, which isn't to say that those 2 values, there won't be a conditional dependency on them. Those 2 will become conditionally conditioned on the data, but at least in terms of if you think of it in terms of the data generating process, you generate the 2 independently of one another. Okay. So basically these are kind of technical. This kind of a technical definition, but I wanted to include it because it's important. The key thing to remember is that we essentially each customer gets 2 parameters, a lambda and a mu. The lambda dictates how often the customer transacts, and the mu dictates how long the customer is alive on the system. Okay, and those are both produced via gamma distributions, and the two values are also independent of one another. So we don't have to model that correlation across customers. Okay. There is a second version, just to put it in there, and this is something we may get to, which is the beta geometric negative binomial. I'm just including it here. We may talk about it in this workshop series. We're certainly not going to bring it up today, but just to show that there's different ways in which you can model this. This comes up, the BGNBD model is a much simpler model to fit, but has its own issues, which is why I'm kind of not working on it yet. But I do know a few people who use this quite well. And apparently, again, going back to one of the ease of use things, one of the reasons why I've heard the BGNBD model is very good is you can essentially build a really simple model in Excel and fit it in Excel, and it's all very fast. But that model is slightly different. The transaction rate is modeled similarly. So we have a lambda for that. But rather than modeling the lifetime explicitly, instead what we have is at every point of transaction, there is a probability P that the customer will stop after that point. So essentially what we do is we wait until there's a transaction, and then when that transaction occurs, we then check to see if the customer drops off. And that's a fixed probability at the point of every distribution. And then we can combine those two together to get an expected lifetime, but that expected lifetime is then dependent on the frequency rate, which isn't true in the PNBD model. Okay, but I just wanted to show that, we can actually, these are components of a statistical model that we can mix and match as we want to fit whatever purposes we need. And apparently I haven't really looked at this in too much detail. I think I've implemented it in Stan when I was playing around with it about a year ago. But it does, you can start doing these different things. One of the big issues I've heard with the BGNBD is it overestimates the churn rate for very frequent customers, which kind of makes sense when you think about it, because if your customer is transacting very frequently on your system, then the customer is also getting a lot more opportunities to churn. Whereas, just by dint of the model. So therefore, highly frequent customers are more likely to be declared churned, purely because they've had more opportunities to do so. And that's something that you kind of have to account for, apparently, when you use these things in detail. So I've just wanted to mention it, that we can do it. We may get back to it towards the end of the workshop series. For the moment, I'm just gonna leave it there. But before we get to that, does anyone have any questions about what we've talked about so far? While I just have a quick cup of tea. Oh, just to mention, while I'm waiting, we will take a break. I usually have these about 2 hours, although really it's kind of about 1 hour and 3/4, because we tend to finish up around 1/4 to maybe 10 to, depending if there's questions or whatever. But I try to finish the content around 1/4 to the second hour. But we will also take a break around the hour mark, depending on how we get on. And I don't really have it'll depend on the questions and how things get explained and all that. But if you have, so we'll be taking a break in about probably around 10 to 11, so in about 15 minutes, but it just depends on how we get on. Okay, I'm not seeing any questions, so I'm going to crack on. All right, so again, we have our data here, and once again, I'm not using real data yet. I'm probably going to introduce real data in the next workshop. So basically what I'm doing here, because we're trying to get a sense for the data itself, what I want to do is build, and it sounds a bit stupid, but it's actually a very effective tool, and it's known as simulation-based calibration in kind of the Bayesian world. So what you do is your model, you treat your model as a data generating process. So in other words, the model that you're trying to fit, you use to generate data from with a bunch of parameters. And then you use your Stan model to try and recover those original parameters that you created. And you try to see if your model can actually do that properly. And in some cases, it doesn't work. And that means there's a couple of things it can do. One, quite often, it's just a great way to debug your code and make sure you've coding errors or indexing, or you've made a mistake with something. There's all these kind of gotchas. It's very easy to come across. But also sometimes your model is flawed, and your model either doesn't have the statistical resolution to be able to answer the questions you're trying to ask, because the way you're generating the data versus the way you're observing the data, and then how you're trying to recover those parameters is just not capable of doing it. And that is definitely can be the case with these models sometimes. So it's a very useful way of getting comfortable with models and allowing yourself confidence in terms of making inference, because you can try things out on your synthetic data, make sure it works in the way you would expect it to work, and then that will kind of lead you better in terms of running it on real world data. So that's basically what we're doing here. We have a synthetic data set that I used, basically generated using these assumptions, the PNBD assumptions. So I created a shape and array parameter for the lambda and a shape and array parameter for the mu. I generated a whole bunch of transaction data, and then I used that transaction data to try and recover the original parameters. And that's basically what we're going to try and do. And that's where we're going to start. It's what we've been kind of doing for the last few months, for the last few workshops. And hopefully by the end of today, we'll be kind of done with it, although we might go back to it for when we start building more complicated models towards the end of this workshop series. All right, so I've generated some data. It's relatively straightforward. I generated some cohort data. So I'm generating some synthetic customer IDs. I'm giving a date at which they first transacted, and then we're kind of using that as the basis for our data. We end up with a whole bunch of transaction data. So we have a customer ID, transaction timestamp, an invoice ID, and how much the customer transacted. And then I have a very kind of visualization of the transaction times. Just, a picture is worth 1,000 words. I always find it's useful to just kind of look at the data and get a sense of how things work. And we can see there, you can definitely see that this is, a reasonably regular data set in that, we're not seeing crazy clusters too much. Oh, I guess this, I don't know if you can see, yes, you can. This kind of middle guy about, 3/4 of the way down, I guess, has a couple of clusters of transactions, but that's somewhat indicative of a low frequency as well. Quite often with low frequency transactions, you will get these tight cluster of bursts of events with then big gaps between them. And then obviously you'll have a bunch of single events as well, but it's not it's not uncommon at all to see that kind of thing. So this is, this doesn't have the usual noisy messiness of real world data, because generating that kind of real world randomness is actually quite a challenge. And I generate a lot of synthetic data as part of my work from time to time, trying to fit models or trying to work on things where we don't actually have the data that we're trying to do. So we kind of generate some synthetic stuff, and it can be quite difficult to actually build in that, just the kind of the mad randomness of reality can be quite a challenge to introduce when you're dealing with, regular probability distributions. Okay. All right, so we have that data, and then we have a couple of routines. And what we're going to work on now is we kind of have our basic model, and I don't normally do this, but I think it's quite important for this particular model. We're actually going to do a little bit of algebra and a little bit of probability theory, because we don't have a nice way of doing this. So essentially, we're going to have to do a little bit of thinking and a little bit of maths to actually figure out how to model the likelihood of observing any data that we've got. So because essentially what Stan needs is a log likelihood model that it then does its sampling inference on. So we're essentially going to produce that, the combination of the prior and the log likelihood model, and then we're going to put the two together, and that's going to give us when we throw data at it, that's going to give us our posterior inference. So what I think I might do is I'm going to go through the log likelihood function. We'll then take a break, and then we'll start using it in the real world when we come back after the break. I think after we've been there, I won't spend a huge amount of time on this, and I won't spend a huge amount of time on the algebra. I just kind of want to give the overall kind of concepts of what we're trying to model here, how it's going to work, because that will inform everything that comes later. And again, I appreciate this is probably a little bit technical, and hopefully it's fairly self-explanatory if you have these slides to hand. I think I pushed everything up onto GitHub, but if it's not up there, I'll certainly do it after this workshop. And you can look at it, you can kind of see it for yourself. And I got this from various things. based around the BTYD packages and stuff that are available on R. There's a whole bunch of links from the Peter Fader website and stuff that has some pretty good stuff on there. Okay, so we have a customer, and for a given customer, there's 3 observations that we've made, right? We know that basically that there is X transactions have occurred over the lifetime of the customer that we have observed it. And we know that the last transaction was T sub X, and that also the total observed period of time from now back to when the customer first appeared is capital T, right? But we also know that there was, T1, T2, T3. So we this is just a little timeline. We have all these different timeframes, even though we're not using them in the model. We have those observations if we need them. So we're gonna use them to try and figure out how to build a likelihood model. So to model the likelihood of this observation, there's 2 possibilities. So there's one possibility where the customer has not yet churned. In other words, that the lifetime of the customer is larger than capital T. And then there is also the possibility that the customer has churned by capital T, in which case that we know that the value of tau, the lifetime, is somewhere between T sub X and T and capital T. Okay. So what we're going to do is those are 2 separate distinct possibilities. So what we're going to do is calculate the likelihood of the first one and then the second one, and we add them together, and that gives us our likelihood model. Okay. We then have to talk about how we can calculate logs of that, but we'll probably deal with that when we get back. Okay. So in the first incident, the likelihood is the product of the observations at each transaction, plus we know that the customer is still alive at time T. So it's essentially the likelihood of seeing all the observations we saw at T1, T2, T3, all the way up, right? And transactions, in that period of time. And again, it's the time between events. So even though we're dealing with a Poisson distribution, we're essentially using the exponential because it's the time between the events. And basically the probability for that the customer is still alive at that point in time. So basically, when we get a bunch of mathematics on this, we have this value here, which is just all the different lambda events between T and Tx. And then lambda x is, oh, sorry, someone's on mute. Oh, okay. And then we have this value here. Basically, there's a whole bunch of arithmetic, but a lot of them cancel. So we end up with this lambda x e to the minus lambda tau, where tau is the lifetime that we haven't observed yet. So we're going to have to integrate that out. Okay. And then in the second case, the customer becomes inactive at some time tau in the interval. So we have something similar, but we just now have to we now have this window in time in which that we know the customer churned in this period between here and here. Now, again, the algebra takes a little bit of getting your head around, and I'm not entirely sure I don't have typos in here. I will create a link. I'll create a link in the break to the PDF, which is really good, which explains this in a bit more detail, where I'm pretty confident that the algebra is correct. But the basic idea is that we're breaking it down into 2 parts, one where the customer has churned at the point of observation and one where the customer has not. And essentially, once we break it up into those 2, it's a relatively straightforward application of the exponential density function to calculate the likelihoods. We just multiply the probability of the customer churning and the probability of the customer not churning by the probability of observing things the way we did. When we get all them together, we have a likelihood model that does depend on the lifetime value, which we then need to integrate out. And then we essentially boils down to this kind of value here, which is a bit of a mess, but it's not the worst thing I've ever seen. And there's no integrals in there. The whole thing kind of integrates out because we're dealing with exponentials. That's probably the reason why the exponential distribution and the Poisson are used here, by the way, because it makes the maths work out nicely. And that is more often a justification and a use for like powerful statistical models than you would expect it to be, because also it means things are computationally efficient in terms of doing it. Okay. So we now basically have, so this is what we're trying to calculate here. This is the likelihood, not the log likelihood. We'll take logs in a minute, but we have basically the likelihood of observing for the likelihood for any given value, lambda and mu, given the three observed quantities, x, t sub x, and capital T. And it turns into this kind of bit of a mess, but nothing catastrophically terrible. And that is basically the observations that we have observed for these values. So this is the likelihood, okay? And this is what we're going to encode in Stan and plug it in so that when we observe and we pass it the values of x, t sub x, and capital T, it will actually perform the inference and give us posterior values for lambda and mu, okay? I think this is a good place to stop because it's about 10 to well, it's 10 to 3 here. It's 10 to 8 over there. What I'm going to do is we'll take a quick break for about 10 minutes. We'll be back pretty much on the hour. But I'll let people take a break, have a think about what I've just said. And if there's any questions about needing to explain it more or getting into it, I mean, I can certainly, and actually one thing I'll do is I'll dig out a link to the PDF where I got it from. It was in the BTYD CRAN. There's a whole bunch of stuff there. And they go into it a bit more detail, and a lot of this is pretty much copied directly from that, because I figured, flattery is, the imitation is a sincere form of flattery. But yeah, we'll take a break there. We'll give people about 10 minutes, and I'll also give people the opportunity to ask any questions in the chat if they have. And when we come back, we'll talk about, now that we have this likelihood model and we have our priors, which are gammas, how do we actually fit a Stan model using this likelihood? How do we encode this into Stan? Bearing in mind that we need to take the logarithms of these, and how do we do the log of a plus b? And we'll talk about that with log sum exponential. Okay, so I think we'll take a break there. I'm going to turn off my video. I'm going to take a quick break. And if anyone wants to take this opportunity to ask any questions, just pop them in the chat and we'll talk about it in the next couple of minutes when I'm back. Okay, so we'll be back up pretty much in 10 minutes time. And I'm back. Oh, hi, Greg. Yes, I've just pushed CLV Workshop. It's not in the main branch. It's under the CLV Workshop branch. You should have it there. I will also dig out that URL for, actually, give me a sec. For where I got all that, where that maths came from. In fact, I think I can just upload a file. Let me see if I can do that. Yes, it's actually it's that, Chris, but also it's because with log likelihoods you get much smaller numbers, whereas you have rounding issues and numerical precision issues because the numbers tend to be very, very small. Whereas when you take a log and do addition, you have much better numerical performance as well. So that's typically another reason for why log likelihoods are preferred to likelihoods. Yeah, and I'm blanking on the term, but it's a monotonic function as well. So it doesn't actually change the relative ordering of anything. So it's mathematically nice to just take logs, and it gives you kind of the best of all the different worlds. The only issue with it is that in these kind of situations, you sometimes get these kind of weird edge cases, but computer sciences came to the rescue as a result. Let me just try and, I'm trying to think, is there a way to upload a file? There usually is. Hold on a second. Let me see what that does. Microsoft OneDrive. Well, we've got a couple of minutes while people are taking their break. I'll see if I can dig it out. Yes, that's it exactly, Amin. Yeah, you just all those problems just kind of go away once you take logs. Let me just. I'll just stop my share temporarily. Is probably the easiest thing to do. Yeah, there we go. I have it. So for those of you who want kind of a more technical note based on this, because I know I was asked about this. Share my screen again. So there's a guy, Bruce Hardy. I think he was one of the colleagues of Peter Fader. He's done a lot of this work as well. He has a bunch of stuff there. There's a link there. If you follow it back up, there's a bit more detail there. So I think I had another question. Just give me one sec. No, I totally understand, Chris. I absolutely want to understand the intuition more than I want to know the detail. Now, part of me could be because I always sucked at the algebra. So, I mean, I could do it, but I never enjoyed it. And I always found that whole thing a big mess. And I was never particularly good at it. So it's also one of the reasons why I much prefer computation. When I'm playing around with statistics, I tend to do things through simulation, and I tend to understand things much better when I simulate them, much better than if I look at like formula. I know other people are different, and some people much prefer to have the answer through the maths. In my experience, that's just not the way my brain works. Oh yeah, I can indeed. Hold on one sec. I'll do that before I come back. Now I don't have. It's on a specific branch, so I don't think it won't until I merge it into master. It won't render directly, but there's the URL for all my workshops, and in particular, it's the hold on the WSCLV Bayes 2022-01. It's in all the stuff is in that folder there. And if you're interested in any of the other workshops I've ever worked on, or talks I've given, or whatever, pretty much everything is in that one repo. Okay. Yeah, I guess we'll get back to it. I haven't had actually just before I do though, I haven't had any internet outages or anything, have I? I haven't noticed anything here anyway, so I'm going to assume I haven't had any. But like I said, even if I do, I'm just going to plow on for the purposes of the recording. It'll all go online, and then once I start seeing things in the chat again about, hey, we haven't heard you for the last 2 minutes, I can cover any issues that I needed to cover. Okay. So yeah, let me just go over that intuition again because it's quite an important one. So we basically have we've three observed pieces of information. We have how many transactions were made since the customer was born. So basically, it's a whole number greater than zero, or sorry, zero or greater, because you could have a customer that's born and has not transacted since. So we have so we have that. We also have how many. What was the time from at the point of birth to the last observed transaction time? So how long, you can think of it as the minimum value that the customer is alive for, because we know the customer is alive while they're transacting. And then what's the period of time between the customer appearing on the system or being born and the current point in time, which is capital T. Okay, so we have those three pieces of information. Now, we know that basically the customer transacted at all these points in time, like you can see here. And what we can do is we can use because it's modeled by a Poisson, we know that the time differences is modeled as an exponential. So the likelihoods of all them is just a bunch of exponentials. And then we have to do the maths around, did the customer churn sometime between Tx and T? In other words, is the value of tau, the lifetime, is the value of tau somewhere between greater than T sub X and less than T, or is it greater than capital T? Right? So, and that's where the differences come in. And once we've done that, we end up with this kind of likelihood expression. This is the expression for the likelihood. Now, like we said, we don't calculate likelihoods though. And basically all Stan is doing in the Stan model that we talked about in previous workshops and stuff, all you're codifying in Stan is a likelihood model. And the likelihood model is then used by Stan to generate the posterior distribution from the data. Okay, because that's essentially what it's sampling from. Okay, and that's done in log space, right? We do all that work in log space for all sorts of different reasons, the biggest one being like rounding error and precision. But it immediately poses a problem because it's very easy to take the log of a product, right? Log A times B is log A plus log B, right? These are all the things we learned in basically secondary school or high school, whatever part of the world you're in. You know, once you're doing any kind of advanced kind of algebra or any kind of things like that, your laws of indices and your laws of logs, that's no problem. However, we don't know how to calculate log A plus B. And because of the way statistics works, we often, when we're modeling likelihoods, we often have to break things down into different conditions. So we'll say, well, there's 3 or 4 different cases that can occur that are disjoint. So it's this, this, and this, and the likelihood is the addition of all three. So basically, the way computer science has solved this problem is it's very common to have this thing called log sum exp, or the logarithm of the sum of exponentials. So essentially what we do is we say that log a plus b is the log of the sum of the exponentials of log a and log b. So when we have a value a plus b, we take the log of a and the log of b, and then we feed them into this log sum exponential, right? And it basically takes the advantage that the exponential function and the logarithm are the inverses of one another. Now, it does something, it's not just a matter of applying that, it does a bunch of very clever things in the background to deal with things like rounding and precision and, you know, very high, very low. Like if basically you get problems when if values are very, very small or close to 1 or close to 0, you get all these numerical issues that a lot of computer science people and numerical analysis people have been dealing with a long time. So typically when these libraries offer this log sum exponential as a library call, they're doing a bunch of things, and it's usually worth using it if it's available. Now, I know that's a very broad statement, but typically they're dealing with a whole bunch of edge cases that you may not have even heard of, and they tend to be give you much better kind of numerical precision than if you don't use it. So we have that, and we're totally going to use it because I'm not proud, right? So essentially we have this value here. So what we need to do is calculate the log of this first piece here, calculate the logarithm of that, and calculate the logarithm of this other one, and then we plug them both in, and that gives us our value, okay? And basically, when you take the logs of all this, again, it boils down to a bunch of stuff, and eventually we get what we can see here. Oh, there's a typo. I didn't put the log there, so I need to add that. Okay, I need to fix a typo there. So this is essentially x log lambda plus log of mu minus the log of lambda plus mu plus the log sum exponential of minus lambda plus mu tx and log of lambda minus lambda plus mu capital T. So that's basically what we're going to feed into Stan and fit our models with. Okay. And again, for more maths, you can either do it yourself. There may be a typo in there. I'm pretty sure that one's the right one though. And I think that's the one I've been pretty much coded and used and seems to work. All right, so we know the synthetic data and we have a bit of code. I've created this kind of helper function that turns transactions data into these, calculates those three summary numbers for us, x, tx, and tcal, which is the capital T. And we're also going to create some subsets. If you mentioned it before, we have a whole load of customers in our data set, but fitting that data can be slow and cumbersome. So instead, what I've done is I've taken a bunch of different subsets of the data, and they're all, the reason why I've done it by a shuffle is they're subsets of one another. So if I want to look at just the first 50 random customers and 1,000 random customers, the 50 customers are part of the 1,000, which are also part of the 5,000, and so on. Whereas if you just do it all randomly, they're all separate from one another. So this is a nice way of essentially growing my sample with wholly contained subsets. That's all I'm basically doing there. I know this might seem a bit weird why I'm mentioning this, because this is actually a gotcha that I didn't do it this way. I used to just take, 50, 100. And what will happen is you're trying to compare one with the other and you don't have a proper reference between them. And for the purposes of debugging and auditing your modeling and stuff and trying to figure out where did I go wrong or what exactly am I doing, or when you're trying to interpret your results, it's really handy to have these kind of wholly contained subsets that you can work on. Because you know that if I'm looking in my 1,000 customer data set, I can also make reference back to the 50 that maybe I know a bit more about because there's only 50 in that one and all that kind of stuff. So I know that's not really relevant to Bayesian stats or buy till you die, but I just thought I'd mention it. So now we have the fit data and we can put it in. And again, I've done this visualization. You can see we have a whole bunch of, if not one transaction, then two transactions close together, and then essentially a churn event. So these are kind of the modeling that we're looking at, and we're going to fit our first model. So we're going to start with the Stan model. Let me just move out a little bit here. So we're basically implementing this in Stan. So this should look broadly familiar to what you had before, what we saw in previous ones where we were dealing with lambda or exponential models or whatever it was. So we're passing some data in. We have n, which is the number of customers. So we're going to loop over that number. We also have this a vector of the three statistics that we have observed: t sub x, the calibration time capital T, and x. And I've used it t underscore cal because I just find capital T by itself sometimes just it's easier to interpret t underscore cal purely from a human looking at it. Again, your mileage may vary. This is by no means specific. And then in reference to previous workshops that we've got, the priors for lambda and mu, I've changed that. So while they're basically a shape and a rate in the model, I've actually changed them into the mean and the coefficient of variation, because I find that's a much more, even though they're not directly translated into gamma parameters, it's very easy to, like, it's an arithmetic transformation. You just use some arithmetic. So what I've done there is I'm thinking my priors, it's much easier for me to think about my priors in terms of the mean, which is like a measure of location, right? And then the measure of dispersion, which is the coefficient of variation, right? Now, it's not perfect. It's not quite as natural as when you've got a Gaussian and you're thinking in terms of the mean and standard deviation, because obviously it could be a big long tail, and the coefficient of variation can do some weird things at times. Yeah, I just think of it. To me, it just makes more sense. I think it's easier for me to set priors using this, and then we just use these algorithms to transform. The other thing I've heard anecdotally, but I have no direct experience of this really, is that I know apparently a bunch of new for some models, they actually use these transfers and they fit these values, the mean and the coefficient of variation, and then transform back into the shape and the rate, because the shape and the rate are correlated with one another because of this, because neither of them are a coefficient of there's a dependency there. So therefore they can be harder to fit numerically, whereas it's easier because there's a certain amount of independence between the mean and the coefficient of variation. The coefficient of variation, for those of you who are familiar with it, it's just the mean divided by the standard deviation. Or is it the standard? No, sorry, it's the standard deviation divided by the mean. So it's like a standardized standard deviation, if I'm not abusing language too much there. All right, so that's we've set up our data, and I'm passing in the priors as data, the values of our priors as data. And the reason why I'm doing that is this is just a pure computing trick. Technically, it isn't data, but it means that we don't have to hard code our priors into our model. If we put the values of our priors in as data, it means we can use the same model over and over again with a different set of priors. And it means we're not constantly fitting different stand models and having to keep a bunch of different executables to keep track of. Instead, we have one stand model that we can throw different parameters at. And that way we get different stand fits based on, and it allows us to gauge, how sensitive our posterior inferences are to the priors and stuff like that. Okay. Because in some cases that will be quite significant. Okay, so now we have two parameters, which are, as I said, two vectors. We have a vectors of lambdas and a vector of mu's. So each customer, and you see there's n, one for each customer. So we have lambda I and mu I, and each customer is customer I, which is a numeric, and that's just Stan works on. Basically, it's C++ at the back end, which is why you've got like the semicolons at the end. And it's this weird mix between Stan and between C++ and OR, because JAGS was based on OR, and JAGS was what inspired Stan. So the language in Stan can sometimes look a little bit weird. So we've set so that's our parameters, and now we get into the main model. So we see we just have that lambda is a gamma based on R and alpha. R and alpha are transformed data from our lambda mean and our lambda coefficient of variation. And similarly, mu is just a gamma of S and beta. And then I've written this function, calculate Pareto negative binomial distribution log likelihood. That's a Stan function that was included up here in this util functions.stan. And rather than write it out in a big mess of a model, I've just encapsulated it in a function. We will talk to that in a little bit about how we implement that. And you'll see that takes a bunch of different parameters, n, lambda, mu, x, tx, and tcal. Okay. And then finally at the end, which we won't get to just yet, and we'll probably get to today, but maybe not, we have our generated quantities. So after the model samples, we can then calculate some derived values based on our sample. And one of the things we're going to look at is the probability of a customer not having churned by the observation time, capital T. And that's something we can calculate from lambda and mu. It's that bit of a mess here. We'll talk about how we derive that a little bit later, but that's a very handy value that we're going to want. So rather than taking lambda and mu and then calculating it, we're actually going to have Stan calculated for us directly. And there isn't much of a computational hit there because it actually does that at the end of the sampling process once the sample has been generated. So generated quantities is generally quite cheap to do because it's not evaluating it over and over and over again when it's trying to generate the sample. Okay, so we've done some user definitions. So I can see here we have this calculate PNBD log likelihood, and essentially in the log form, that was the version that you would have seen in the previous one. It's basically I'm coding up. One thing to pay attention to though is because it's essentially vectorized, this multiplication is a pointwise multiplication. So when you have dot star, what that basically means is if we take a vector and we have another vector, they have to be of the same length. Dot star just does a multiplication of each of the two values and returns a vector of a similar length, right? So it's a pointwise multiply, there's a pointwise divide. So because Stan has vectorized its code, so it allows for like linear algebra and matrix multiplication natively in the language, there's sometimes a little bit of gotchas over making sure that the operators you're using are the right ones. Okay, so I just wanted to point that out, and that's why you've got these kind of weird dot slashes and dot stars and stuff like that. So I appreciate it's probably a bit to take in and it needs a little bit of digesting, but you can see there it's not actually that complicated to actually write the code. Now, the thinking behind it had probably a fair bit of brain power, and it certainly wasn't my brain power. I'm just kind of implementing, I'm standing on the shoulders of others. But in terms of coding things up, it's not too bad, which is great because it means the simpler your code can be, the less likely you are to have mistakes in it. And in these kind of more complicated, when you're doing statistical computing, that kind of simplicity can be highly valuable and highly prized. But yeah, so that's kind of that's one thing I definitely appreciate. But now we've done that, and now we can just compile it. So I'm using a piece of code called command stan r. Now I've kind of switched over from rstan to command stan r. There is also pystan, and there's for Python, and there is command stan py, I think it's called. So there's two different versions, and it's kind of due to the way in which the model evolved. Just to quickly explain it. So there's rstan and pystan, and what they do is they actually embed the stan executable, because stan essentially takes a stan model and creates an executable binary that runs the sampler. What pystan and rstan do is they actually take that and it runs inside the Python and R process. It's actually in memory, and that has a bunch of benefits, but it also causes some weirdness. So typically what happens is that the stan version lags a couple of behind, especially rstan. I'm not sure about Python because I haven't used Python in a while. Whereas what command stan py and command stan r do is they use command stan. So they basically are a wrapper around the external executable. So what happens is the R process takes the stan code, actually creates a separate binary executable that then runs when it's fitting the model, and then reads the output back in, and it's done in two separate processes. And that's much neater when you're using RStudio. One of the issues rstan has often had is it gives you weird errors because it's some weird interaction in the process space between RStudio and Stan. So I kind of switched over. I get the best of both worlds. It does have a few weird traits though, and it's not fully feature complete. There are things you can do in rstan that you cannot do in command stan. Just in terms of integration with R and stuff, but for the most part, it works fairly well. So that's kind of why I'm doing it. So you pass in some stan code, you pass in the file, I've put all my Stan files into the Stan code directory. I've got an include paths, which tells me where my include files are. So you can see here, I just did include util functions. Basically, that's telling it where to find that file. Pedantic is true, so it gives me a very pedantic output for my Stan code, which is really handy because pedantic is a great way of finding bugs in your code. It's like if anyone's ever compiled stuff in C, you generally turn on your pedantic warnings because it's a great way to catch bugs. And then where do we put our model output? That's what dir is. So there's like 4 parameters that we put in. It creates the compile value, and then we can run our data with it. So I'll just explain that code. So now what we have basically an executable that will take our data and produce a posterior, but we haven't actually ran the model yet. We've just created the code that will run the sampler, if you know what I mean. So that's called fitting the model. We've now compiled the model. We now need to fit it. So we're going to create the data. I've got a customer ID, X, TX, and TCal, and there's this nice function called compose data, which is in the package called tidybase, which basically takes data frames a table and converts them into nice formats handy for Stan, and it means you don't have to redo that work over and over again, which is, again, a great source of errors. I really recommend using it. It's really good. I'm sure in PyStan there's probably an equivalent for those of you who are Python users. But basically what that does is it creates a list of data that's amenable to be used in Stan in a nice, obvious way. And it does all the indexing and all that. It also has the benefit of encapsulating like customer IDs, because Stan can't handle strings. So instead what it does is if you've got like a whole bunch of customers and they're all indexed, it will remember what customer is what index, so that once you've got your model fit, you can essentially recover all of that. And I'll talk about that in a minute. Now we're putting it, and the final thing we need to do is, as well as composing the data, we're also adding our prior value. So we're going to say that the average customer has a lambda value of 0.25. So on average, customers transact once a month, once every 4 weeks, once a month, and that the coefficient of variation is 1. So there's, a broad amount of ranges. I think it basically means it goes from 0 up to about 4 to 10. I can't quite remember. You can run some simulations to check that out yourself. And sometimes with these modeling, because they're encapsulating your prior knowledge, you're not necessarily using the data, but you're kind of building in, okay, well, I know a customer transacts. It's kind of ridiculous. I know I can't have a customer transacting like at a frequency of 1 million, right? So there's no point in having your prior that says that. So setting your priors to be sensible based on like physical constraints or real world knowledge or domain knowledge or whatever, that's actually a really good way to get your model to fit well, because what's more likely to happen then is the data observed and your priors are going to agree with one another. So as a result, your fit is more likely to be valid. Whereas if you have the data that disagrees with your prior, so your data is saying one thing and your prior distribution is saying something completely different, you'll get these weird problems with your probability space, and that manifests itself as divergent transitions and various other problems that you get. Okay, so it's good to have reasonably well-crafted priors. They don't have to be very narrow, but they should just be within the range of reasonable values that you would expect to see, and then you let the data fit the values based on that. So once we've done that, we have to put a bunch of parameters in. We have our data that we've generated. We want, how many chains for the warm-up. We want 4 chains, 500 iterations in the warm-up, 500 for the sample. So essentially our posterior distribution is going to be 4 times 500. So 2000 iterations in our posterior sample. We set a seed. I always set a seed for any kind of random process because it means things, you can there's a certain level of reproducibility. I'm including the warm-up. I'm saving the warm-up in this because it's handy. In other cases, it isn't kept in. And then just some housekeeping in terms of what we're going to set the output to, and we're going to put a prefix on it, that kind of stuff. What we're going to call our output files, that kind of thing. Now, just quickly, because I know I mentioned this before, but I think it's worth reiterating. What happens with the Stan sampler is it uses what's called Hamiltonian Monte Carlo. So it uses Markov chains, but essentially uses ideas from physics to simulate a particle moving through a potential. So it's got momentum and position. It uses Hamiltonian dynamics to model that particle through phase space. So it's like a ball moving through a potential, or a charged particle, or something like a mass moving through a gravity well, all those kind of ideas. Really, really well understood problems. Loads of mathematical kind of numerical techniques. And a lot of this was done by a guy called Michael Betancourt, who wrote a lot of like the physical simulations internal in Stan. And essentially what it does is the positions in space are basically the positions in the posterior, and those are what we sample for our output. Now, in the old days with JAGs and stuff, you had to do what was called burn-in, they called it, which was the idea is that you start in a random point in phase space, explore around until you find where the areas of non-zero probability are, and then you explore them together. In this case, that doesn't generally happen because we're using Hamiltonian. So because we have gradients, we actually kind of know how to go uphill into areas of higher probability. So the particle tends to actually find what's called the typical set, which is the space that we're sampling from, quite quickly. But what it uses the warm-up for is the adaptation process, because that, efficiently exploring the parameter space takes a bit of fine-tuning of the parameters, and there's various internal parameters that need to be fine-tuned. So the adaptation does a lot of that work, and then once that's done, we start the sampling. So it's not quite the same for those, because I know there's a couple of people in the audience here who have used JAGs in the past. While it's a similar concept in terms of, we need to burn in for a bunch of time and then sample, what's actually going on is different. It's using that differently. So generally speaking, most people recommend that unless you have a good reason not to, your warm-up period should be the same period as your sampling, because you just end up with much more efficient sampling from a computational point of view. It doesn't really change the validity of the sample. It just means that you're efficiently exploring the space in terms of your computation. All right, so once we've done that, we have a probability. We're basically fitting. You can see here, this is what the output looks like. There's a whole bunch of chains. We're doing some warm-up, then we're doing some sampling, and then we end up with some summary statistics that have, we can see we have 3,000 parameters. So we have 1,000 customers. We have a lambda and a mu. That's the first two parameters. That's why there's 2,000 parameters. And then the third 1,000 is the probability of the customer still being alive, that generated quantity, that gets included in the sample output as well. So that's why our sample actually has a 3,000 parameters in the output, but just bear in mind it was a 2,000 dimensional space that got explored, if you know what I mean, because that third quantity was just derived from lambda and mu. Now, as I've discussed before, we have to make sure that our posterior sample is valid. We have to make sure all that works. So there's divergent transitions, there's all those kind of things. We're going to do some quick validity checks. So we'll do what's called like the caterpillar plots, which is a plot of the trace of all the values. I've just included the warm up there. You can see the first half were warm up values. We'll get rid of them later. And when we get rid of the warm up, we can see, yeah, I mean, what we're looking for here is what's known as geometric ergodicity. So that is one of the things you need to ensure that the posterior that we have obtained has, it's not so much that we've proven it's correct, it's that if we don't have geometric ergodicity, we know that it's wrong. So it's a bit like, proving the contrary thing. What geometric ergodicity means is essentially at any point in time, there's no point in terms of how many samples we've taken, does the probability distribution kind of look the same? So for the purposes in practical terms, it means when we do a trace plot, is it rotating around a constant value, or is it moving up or down? If it's moving up or down, we know that ergodicity has been violated because there's some kind of a drift in the sample, and it basically means our sample is invalid. We're not doing correct sampling. So we need to walk back from that. And you'll also get, there's a whole load of different diagnostics like divergent transitions and stuff like that. I've talked about them in previous workshops. We're probably going to meet them again in the next workshop or two. So I'm not going to go into too much detail on that now because it's a big problem that you have to solve, but it's a bit like debugging, right? every problem is kind of unique, and all we can really, there's no tricks or there's no technique to solve them. All you can really do is, here are the types of things to look for, and here are the types of things that you might want to change or to let you know that there's a problem. Okay, so that all looks good. They're basically flat around a constant value, and now it's just a sample of 4 customers. So we have 4 values of lambda, 4 values of mu, but they look okay. Our split R hat as well, and is a value. It basically, again, it's kind of sampling based on the values that have been checked. It's basically a way of checking that across the different chains, and within the chains, is there any correlation between the two? And there shouldn't be. It's a measure of similarity. Ideally, you want the chains to be at 1 or very close to 1 statistically. These are all quite good. It used to be 0.1. I think they've kind of made it stricter than that now. I think they want it to be less than 0.105, and this is just a very quick plot of every single parameter in the value. We can see that all those R hat values are quite close to 1, so that's pretty good. Oh, one last thing. The 3001, I never mentioned it, and no one has actually asked it. I'm sure I probably will get the question. Well, what's the extra parameter? The extra parameter is just the log probability. So if you look here in the sample, we also calculate what the log probability was. So the sample, the output of the log probability model is also plotted as part of the output, and that can be handy for a bunch of other things that are used for like diagnostics. So Stan produces it at Matter course. So you'll always have this extra, at least this extra single parameter, which is just the log probability of the output. And they produce all them as well. Well, I've never really had to use it for diagnosis purposes, but I know it probably could be used. Tied into the R hat value is this thing called the effective sample size. So I can't remember if I talked about this in previous workshops, but I'm going to mention it again because it's quite important. So essentially, because it's a Markov chain, this sample doesn't provide. If you have a sample of size n, as in n separate data points, then if those values are all independent, then you have n points of information, okay? And each of those are equally weighted. So if you think of it kind of like information theory, we have n points of information that we can use to perform our inferences. When you're dealing with a correlated, when you've got autocorrelation or, like Hamiltonian Markov chain, when you're dealing with a Markov chain, you expect a certain amount of autocorrelation in the parameters, which means that the effective sample size, so even though we have n data points, the amount of like statistical data points we have is different to n. And it could generally it's much less, because there's a certain amount of information. Each new data point isn't giving a full data point worth of new information, because of the correlation, it's kind of encoded in the previous parts of the trace. But in some cases it's not. It's actually greater than 1 because the autocorrelation is negative and you actually get more information from each data point. So it works into the statistics. Again, a lot of this goes over my head, but I read a bunch of things on the Stan forums, and then I start to accidentally learn through no fault of my own way more about statistics than I probably had any right to know. Just again, standing on the backs of others. But essentially, what you're trying to do is you want a good effective sample size, because the more, again, larger sample sizes are better. And if you're going to spend the time calculating 4,000 data points in your sample, but your information size is only 100 data points worth, well, that's quite an inefficient sample. So that's not necessarily good, and it probably tells you have a problem with your model. So the effective sample size is a very good way of doing it. And in particular, what they calculate is the ratio of the effective sample size to the actual sample size. And ideally, you want things to be greater than 1. And in this case, we have a nicely well-behaved model, so we have a very good sample size ratio. But quite often what you'll find is you'll find a whole bunch of data points down here between, say, 0.5 and 1. You generally don't want anything lower than, I think it's 0.3 or maybe 0.25, but it really just depends on your model and how well you're doing, and how how much statistical noise is in your data and if things are correlated and how messy your model is and the quality of your data, all that kind of stuff. I'm not going to bother with the autocorrelation lags, but those are also some things to do. So now that we've done that, okay, we can kind of cheat, okay? Actually, before I move on, has anyone got any questions? Because I realize I've thrown an awful lot at you there. Just give me a sec while I catch a chance to have a cup of tea, sip of tea. So we've taken our log probability model, we've encoded it in Stan, we've used that Stan model to compile a Stan executable that can run all the numerical stuff. Once we have that, we can then throw data at it to fit our model. And now what we've done is we've assessed the output of our model to ensure that it's a valid statistical sample of. So in other words, is the thing we're sampling actually what we thought we were sampling? And that's a big issue for reasons I've discussed in a bunch of previous workshops. And that's why Stan came about, because they found flaws in JAGs, and you've got these things like the non-centered and centered parameterizations. It's relatively easy to create probability Stan models where you get loads of divergent transitions, and while you have a posterior sample, that posterior sample is not actually the posterior that you thought you were sampling. It's biased, and you're not getting the proper probability distribution that you think you're getting. And that's what we have to check for. Okay. All right. No questions? I'm seeing a thundering silence, or have I gone quiet? Neil, will you just ping me if you get this? Will you just put a chat in just so I know that our connection hasn't died? Hello? Ah, okay, great. Cool. Okay. Yeah, I'm a little bit paranoid that, the internet has gone out and I'm screaming into the void here. Okay, so we've 25 minutes left technically, probably in reality, somewhat less than that. So we can now finally start assessing our model, right? And we're going to cheat because, as I said, we're using a synthetic data set just to get some intuition about the models. So we know, because I used synthetic data, I generated using a gamma distribution, I generated for this data set that we've just used to fit our model with, I generated a lambda for every customer and I generated a mu for every customer. And I can compare them to our posteriors. So for every customer, we have a 2000 sample posterior distribution for lambda and for mu, and we know what the true value is. So what we can do is this thing that we talked about in previous workshops. We can basically create an ECDF of the posterior distribution, an empirical cumulative density function, or cumulative distribution function, I should say. We can place the true value on that, and that gives us a value between 0 and 1. And ideally what we would have is, if we have if we have a valid statistical process, in other words, if our posterior distribution is properly capturing that parameter, that distribution of Q values should be roughly uniform, because we don't expect everything to be in the middle of the distribution. We would expect some values to be way off in the tail, either to the low end or the high end. So that's basically what we're doing here. Now, we won't be able to do this in the real life, and we're going to have to come up with alternatives. And that's something I'm going to talk about just before I let you all go. But basically, we can see this is the values for lambda. So it's pretty good. Like we have, so there's 1,000 data points in this. For every customer, we have the true value of lambda. We have 2,000 posterior samples for lambda, which we use to build an ECDF. We place the value like on the x-axis, move up and see what corresponding value of y. So if you can see, I never turned on my screen. Let me turn my video back on. My apologies for this. I should have turned this on ages ago. So if you could, I'm just looking at myself here. I'll do it this way because it'll make more sense, I guess, because I'm looking at myself inverted. So we, an ECDF will this kind of S curve. So we have our value we observed. We move up to the line and move across. That gives us our Q value, which is a value between 0 and 1, because it's essentially a probability. It's the probability of that value being less than or greater than given the probability space. And we would expect that to be uniformly distributed from 0 to 1. Okay. And as long as we get that, then we're reasonably happy. And what we see for lambda is that it's true. right? That we're actually reasonably happy that we've observed that. For mu, it's not quite so good. We've a bit more of a bunching in the middle. So we're not really getting the extreme values of the lower end of mu and the higher end of mu. We're getting a bit more bunching in the middle, but it's still not too bad considering that it's, like I mentioned before, we can kind of observe lambda because we know exactly how many transactions occurred. The lifetime is more unobserved. We kind of pigeon it in between two values, or at least one minimum value. So we would expect there to be less resolution around mu than lambda. So that is kind of matching our intuition. But let's try that. So we've done that. So it's not too bad, right? But the benefit is, you know, we don't necessarily know what the probability distribute, like what those priors should be, right? We kind of guessed them. But what I kind of wanted to try is how sensitive is our posterior inference to those priors. So it's basically just a matter of rerunning the code. So let's say I put in a bigger coefficient of variation. So I have the same mean for both, but instead of using coefficient of variation of 1, we use 2. We refit our models, and what do we get? Right? Well, we've got, you know, I didn't want to check the model fit, but now we can see that the lambda values aren't as good, because what's happening now is our coefficient of variation is higher. So let me explain what's going on there. So basically, because we don't have a lot of information on each customer, most customers don't transact that often, right? So we don't have a huge amount of information to perform inference on mu or on lambda, right? So as a result, the priors are relatively important. And I've created a little r gamma underscore mu CV, and this is in the data. So let's create 1,000 ones, right? A mu of 0.25 and a coefficient of variation of 1, and just plug that into summary. I'm assuming everyone can see that. Let me just get a bit bigger on this. Right? So we see here I've basically created this little function. What it doesn't do anything special. It basically does that mu coefficient of variation transform that I mentioned in Stan. It does it in R, and then it samples from a gamma, right? So it's just doing the same thing. So we can see here that what this is saying is that customer ratios are going to be roughly somewhere between 0 or very, very low and say 2.5, right? Which, you know, isn't too bad, but it's, you know, it's, and that, you know, the highest value we're observing is 2.3. So roughly 2.5 transactions a month. Okay. Somewhere between those values, right? And the customers have that lambda. Okay, well, let's try it with the CV2. So now we see the max is much higher, but we also see the quantile is lower. So we get kind of weird effects when we're starting dealing. So this is the other thing, that problem with setting our priors, is that because we're fixing the mean and we're changing the coefficient of variation, as the coefficient of variation happens, right, we're fixing the mean, which means to get to the longer tail, we're also going to have a lot more small values. So we're essentially creating lambda inequality, right? So we've got more customers with very, very low numbers and more customers with very, very high values as well. And although but the mean isn't really changing, right? It's between, and that's because we've only got 1,000. Let's put more in. Let's say we do 10,000, or what's that? Is that a million? No, it's 100,000, right? So 100,000 in there, you see we're getting much more extreme values. The mean is pretty close to 0.25. The median is less than 4, but the median here is much higher. It's 0.17. So that's just one thing to be a little bit wary of when you're setting your priors, is that the priors can have an effect. And what's happening here, I think, is the reason why when we go with the higher coefficient of variation, what's happening is we're putting more probability mass at the higher end of the lambda distribution. So lambda, there's a higher likelihood, according to our model, of customers having higher lambdas. So as a result, it's more likely to see them up there, especially if you don't have a lot of information. And while the regular, that's what the hyperprior is doing. That parameter distribution for lambda becomes very relevant when we don't have a lot of observations for a customer. So if we don't have a lot of observations for a customer, and let's say it was a relatively narrow time frame, then it's more likely to see it up there. But the flip side of that would be also true. If we had a lot of information that suggests that those high values of lambda are unlikely, then we probably would end up with a mismatch in our distribution, and we'd start to see things like we would start to see kind of weird divergent transitions and all that kind of stuff. Is it ever reasonable to bias the values one way or another on purpose? Yeah, absolutely. It absolutely is. So if you have, so let's say, for example, when you're modeling your data, you don't really, I'm not saying that so there's a certain amount of like scientific purity around, don't let your data, you're essentially double dipping your data if you use it to build your model. I've always thought that was kind of nonsense. I mean, I'm not saying you do, because you don't want to overfit your data either, but you kind of have to use your knowledge of the data to try and make sense of fitting a model based on it, right? But if you, for example, if you are pretty confident in your data that there's like, let's say there's two types of customers you have, and you don't necessarily know which one you have, and you have a bunch of customers that are very, very low frequency, and you have a bunch of customers that are very, very high frequency, then maybe you want to build a prior that matches that in your data set, right? So you would build some kind of, you would set up your parameters in such a way that would, bias, so like essentially a high coefficient of variation. Or maybe you play around with your means, or maybe you subset your data and you actually build that into your model where you have two types of customers and they have two different sets of likelihood. So this, you can start getting, because Stan lets you actually build your own likelihoods, you can actually get very powerful in what you do. Now, the trade-off is it's much more complex to implement, but you do have an awful lot of freedom in what you implement. And the other key thing, which I know I hammer every month, but it's really, really important, is it doesn't let you get away with making lazy implicit assumptions in your model. You have to be very explicit about what you're modeling. And lazy sounds pejorative, but it's very, very easy to use models. Like linear model is a great example that has a bunch of inbuilt assumptions into the model that you're not necessarily aware of, that can significantly impact how you need to interpret the outputs. And if you're going to make those assumptions, you should be very explicit about those assumptions. And these kind of approaches force you to be explicit in that way. And to me, that's good because it means that you do a higher quality inference as a result. But again, it comes with swings and roundabouts, so it doesn't necessarily always work that way. And you can see there in general, like the higher values for that. But what I'd also like to do, and what I was going to do, and this is one of the great things about coding, but I actually realized there's no point in doing it. What I was going to do was basically wrap all this code and all that other stuff into a bit of logic that would let me create 5-10 sets of priors and run the inference on all of them, like create a whole bunch of posterior samples and then calculate these summary statistics and compare them. I will get to that in a sec, Chris, because that's an important point. Okay. Yeah. But I didn't want to. I decided not to go that route for one very, very specific reason, and that was this kind of model of assessing, this approach to assessing our models isn't necessarily a very realistic one longer term, because I'm relying heavily on the fact that we know the true answers, and it's a way of essentially assessing the different models, knowing true answers. But in reality, we actually need to assess our models not knowing the true answers. So we need other ways. We need to be able to basically take the data back to take the models back to the data we have observed and somehow assess that. So, and that's what I'm going to script up probably in the next workshop and try and start, using our different priors for that, basing it back to the real world example. Okay. Yeah. So I will answer. Yeah, I'll actually mention now. So I'm saying the word bias. So basically, what happens in particular by it depends, and I'm overloading the term there. Basically, the first time I was using bias was what can happen with Stan is that if your sample isn't valid, you don't end up properly exploring the full probability phase space. Because what happens is you basically end up with these different regions of the probability space that you're trying to observe. And you end up in one region, and it can be very difficult for the sampler to transfer from one value to from one region of the space to another. And what typically happens in that case, the canonical example of that is the 8 schools problem, which is the kind of the hello world of hierarchical modeling. That it was New York schools, I think, and there was 8 school districts or 8 schools, and it was some standardized testing values, and you had 8 schools in them, and you didn't actually have the individual test results. You just had, you assumed there was a normal distribution of test results, and you had a mean and a standard deviation. And then what you were trying to do with the hierarchical model was you said that the mean of each of the schools was drawn from a hyper distribution, and essentially it was a way to partial pooling to essentially regularize the outputs, because you had a couple of extreme values in there that didn't really make a lot of sense. So it was a way of essentially regularizing the true value based on what we observed. The problem with that was that when you actually build it in the kind of the obvious way of doing it, you end up with what are called these divergent transitions. So basically what happens is because you've had these hierarchical models and you can't properly, the numerics of it is such that you end up with these areas of the posterior space that the sampler can't get into because the curvature becomes infinite. I won't get into the exact details of it, but basically you know that there are parts of your probability space that you cannot get to. Okay, so your sample is biased, as in because there are parts of your sample space that your sampler was not able to explore. And those aren't just technical points. If you look at the 8 schools problem, the original answers that they were drawing inference from gave the wrong answer. And when they fixed those problems, now it wasn't massive. I think the parameter went from being something like 3.5 down to 3. But it was big enough on relative terms. And the problem with it is, and this is why people always ask the questions, how many divergent transitions am I allowed to have in my sample before I can use it? So the answer to that is you have to have a zero tolerance policy of it, because the only thing you know for certain when you have that is that your sample is biased and therefore it's wrong. And the big problem with that is you actually don't know how biased your posterior is. It could be a very, very small and inconsequential part of the phase space that you weren't able to get into, but it also could be where 90% of the probability mass is, and you have no way of knowing. So the only thing you can know for certain is that the sample I have is not a valid sample of the probability space. So therefore, any inference I make on any of the parameters is going to be a biased inference, and therefore it's going to be different from the true value that I'm trying to make inference on. So that's what I meant by the first one. I sometimes use bias loosely as well, is if I'm trying to tweak my priors and I'm trying to capture extreme values or very, very small values, or exactly, and it's random as well. Because the region you're exploring can be reliant upon the random place in the phase space where you sampled. And what typically happens with hierarchical models is you get what's called the funnel. So it's a guy called Radford Neal, who was one of the first people to start talking about using Hamiltonian Markov chain Monte Carlo in kind of computational statistics. So basically what happens is, if you can kind of think of it conceptually, you're kind of narrowing down to a point, which is the group mean. And what happens is it gets smaller and smaller and smaller. So the sampler has to work harder and harder and harder to kind of get in there. And eventually it fails. And you get these weird numerical errors that are clearly wrong. You can kind of think of them as like your numerical simulation is failing because your numerical rounding is broken, and that tells you that you've got what's called a divergent transition, and that tells you that you have a failed. Essentially, your sample is not a valid representation of the probability space you're trying to model. Okay, I hope I kind of explained that well. Okay, so I'm going to hang around at the end because I'm conscious we're getting close to time here. So basically, what we're going to do in the next session is, I'm just looking at the difference between the two. You can see definitely at the higher end, I'm comparing the two posterior space is there. There is definitely a sensitivity in the model to our priors. So we do need to pay, because in some cases, I've done a bunch of work and the priors don't really matter because you have so much data in your model, the priors essentially get washed through by the likelihood. But and sometimes it's good to know that you don't have to, as long as your priors are reasonably sensible, you don't really need to worry about it because your inference is going to be the same as long as you don't give it crazy priors. And I did that. That was one of the ones I was doing with in insurance, which is what I work. I was doing like a frequency model, and I spent a bunch of time and a bunch of effort creating all these different priors and running my sample, and I basically got the exact same answer in all of them. It didn't really make a difference, but it's good to know that. And in this case, that is definitely not the case here. So we can see here, this is just a quick error bar plot of the 10 to 90 and the 25 to 75. That's what these bars are across the different plots here. And you can see there's definitely the posteriors are giving us a much higher value for lambda when we have that higher coefficient of variation in the prior. So the point I'm making here is that we need to pay attention to the priors because the priors will affect our inference. So we need to be pretty confident that the priors that we're giving it are valid. Now, the flip side of this is what we can do, and this is something we'll look to do later, is if we don't really know these values, the Bayesian method is to put a prior to add it to the model. So you capture whatever uncertainty you have and you embed it in the model. So in this case, rather than actually putting in specific priors for the lambda and the mu, we can actually make those priors parameters in the distribution and create a proper hierarchical model, and then allow the data to tell us what those prior distribution parameters should be. And that's ideally where we'd like to get to. That can cause problems though. And that was where kind of I started having issues with these models. And that's something where we were going to start to get divergent transitions, and how we deal with all that is probably going to be the focus of next week or next month. Yeah, and we're going to talk a bit more. So what we're going to do next month is we're going to start using real world data and ignoring the real values. And we're going to basically start using only the data we observed, not the data we knew we had, to try and assess our different models. And one of the key values on that is the probability of any given customer having not churned, as in the probability of still being alive at the observation time t. We're going to use that. That's kind of a key kind of summary of lambda and mu. So we're going to talk about that a bit more in the next workshop. And yeah, I'm probably going to leave it there because I'm pretty much up to time. And I get this is, this is what I mean. So this is, in one sense, this is a relatively simple model. Like, it's not particularly complex in terms of regression. Like, if you actually look at what a linear model is doing, it's actually quite sophisticated. There's a lot going on there. This is really just kind of a fancy schmancy probability distribution, and we're just fitting the parameters of it, right? So what we're going to do, but what I did find is there's actually a lot more going on, and we can actually tell quite a bit. Like next month, when we're using this model and trying to actually do like validate it and use it in the real world, we have quite a bit of information, even though in one sense it's very high level. We just have a frequency for each customer, a lifetime for each customer, and the probability of a customer having not churned. Even that by itself is going to tell us quite a bit, and we can do quite a bit with it. It's going to be quite useful to look at, just in terms of how much other customers we have our inferences relatively consistent on, like does it have relatively tight posterior distribution, or what about the customers we don't really know much about? Why don't we know much about them? Can we focus on them? All that kind of stuff. This I've been thinking about it since, and like I said, this is somewhat of a work in progress for me as well. I don't have all the answers, and I'm sure I've made some mistakes. If any of you are going through my code and there's something you don't understand, please get in touch with me and either ask me to justify what I did or point out where I've made a mistake. It's definitely entirely possible. But I think I'll leave it there. I'll give people time for a couple of questions, and then hopefully I'll see you next month. Oh, and just to let you know, we will have a talk in person at the end of the month. For those of you who are located in Dublin, we have a talk right at the end of the month. I think it's like September the 28th or 29th. It's a Wednesday, and it's a talk on causal inference. The details will be going up at some point in the next few days. It's a guy from Deutsche Bank who's given the talk, and it's based on some research he does. It looks really interesting. And he's going to introduce the topic. It unfortunately will not be hybrid, unfortunately. I don't, well, at least it isn't as of right now. It's only in person, but it's possible we will be recording it. If it is, I will definitely let you know. But anyway, I'm gonna let, if anyone wants to leave, I'm gonna hang around for a minute or two or a couple of minutes. I'll tell you what I will do though, is I will stop the recording so that if people have questions, they can certainly ask them without them going up on YouTube. But otherwise, thank you all very much for coming, and I will leave it there. Oh, let me stop recording. Whoops.